Hello everybody and welcome. Today we will be discussing infinite limits and limits to infinity. So for my class this would be section 2.4 of our textbook. So let's go ahead and get started, okay? Alright, so in here it's a little hard to see, but I think you guys can manage to see this. First we're going to talk about infinite limits, okay? So let's do an example so you understand what it is that I'm talking about. So first of all, it says go ahead and grab the function of 3 over x minus 2 and then find the limits below, and I will rewrite it because it's kind of hard to see. So right here we have a rational function which is 3 over x minus 2. This means we have a vertical asymptote at 2 and a horizontal asymptote at 0. Cool. Now, to come up with a relative sketch of what's happening here, you can plug in some numbers like you can plug in 3. 3 minus 2 is 1. 3 divided by 1 is 3. So that means at 3 you're at 3, which then means that this graph probably looks something like this. So it's just a rough sketch. That's all we really need. And then if I plug in 0, I get 3 over negative 2, which means it's a negative number, which means it's going to be something like this. Okay, so here's what the graph looks like. Now, we can answer the questions. That's a little hard to read, but this one right here basically says what is the limit as x approaches 2 from the negative side of 3x minus 2. So that means that from the negative side, as I'm approaching 2, I am going towards negative infinity. And this one says what is the limit as x approaches 2, but from the positive side, so of x minus 2. So from the positive side, as I approach 2, I am going towards infinity. So here's what I mean by infinite limits. Your answer is going to be infinity. Okay? So the number one strategy, honestly, is first of all for you to recognize that you're dealing with a limit that's going to go to infinity. Is you're going to be dealing with a rational function. Okay? So some type of fractional function, and which means that you're going to have vertical asymptotes, and that's the reason why you can have the answer as infinity or negative infinity. Okay, now notice how these two limits were one-sided limits, but overall, if I were to ask you what is the limit as x approaches 2 of that function, the answer would have to be does not exist, because the left and the right side behaviors are different. Okay, all right, so for the next one, I've used this notes in the past for my pre-calculus class, so I think you guys can kind of get the hang of it right now. So we're going to go ahead and skip number 2 and number 3 because they're very similar to one number 1. I don't think we need to waste your time doing examples that you already know how to do. So let's go ahead and move on to the following. Okay, so you've got this function right here, which is 3x plus 2 squared. Okay, so it's negative 3. Now they're asking you, what number would give you a problem here? Well, the x value that would give you a problem would have to be negative 2. So what I'm interested on is finding out what the limit as x approaches negative 2 of negative 3x plus 2 square is equal to. Okay, so we have a couple choices, right? Remember, with any limit, the very first thing you should always attempt to do is to plug in negative 2. Now, we plug in negative 2, that gives us a 0 in the denominator, which means that algebraically it's not going to work for us. Now, if you had the opportunity to use any of the techniques that you previously learned, then you're welcome to try and go ahead and do that, but at this point there's nothing else I can do. Okay, so really what I would recommend at this point is for you to recognize that if you have something on such that you have a 0 in the denominator, it is very likely that you have an asymptote, vertical asymptote. So to further explore this, I would recommend that you graph this. And when I say graph, I don't mean like an exact graph. I just mean like come up with a quick sketch, okay? So at negative 2, we're going to have a vertical asymptote, okay? And we would have a horizontal asymptote at 0 because it's a bigger denominator, okay? Now, when I graph this, if you plug in some values, so if I plug in 0, 0 plus 2 is 2 squared, is a positive number. Negative divided by positive is going to give me a negative number, which means that this part of the graph would probably be somewhere down here. And because this is negative and this is a square, no matter what I plug in, this is always going to be positive. So negative divided by positive is also going to be a negative, which means that this graph is going to look something like this. So at this point, then, if the graph looks something like that, it's very simple to answer the question. Now, this is asking you what is the right-sided, what is the left-sided. So the right-sided and the left-sided are both negative infinity. Therefore, the answer for the overall limit should be negative infinity. Okay? So let's kind of summarize here what I meant by infinite limits. Your strategy, oh, I apologize. Your strategy here, it is going to be to, anytime you are dealing with a rational function and any of the techniques that you've previously tried before do not work, you will graph or give yourself a quick sketch of what that rational function looks like and observe both the left and the right behavior to find that limit. All right, we're gonna give another example here, so you can have a little bit more practice on this. So if you want to try this on your own, I would encourage you to pause the video and give it a shot on your own, then hit play when you're ready. Okay, so I'm gonna assume that you go ahead and try this. So the very first thing I'm gonna try to do is just plug in 1. So if I plug in 1, we're gonna get 1 squared minus 3, which is negative 2 over 0. So that lets me know, hey, there's a problem here. And I honestly don't see anything that I can try to factor the denominator, the numerator, but it's not going to cancel anything with the denominator. So maybe none of my algebraic techniques are going to help me here. So maybe graphing this would be a good idea. Okay. So what I notice here is that yes, I'm going to have a vertical asymptote at x equals 1. But what I do notice is that the denominator is actually smaller than the numerator, which means I'm going to have a slant asymptote at, well, we need to figure it out. So to figure out and find the slant asymptote, remember from algebra 2, you actually do a division. So x squared minus 3x divided by x minus 1. X goes into x squared x times, so that will give you x squared minus x. We're going to go ahead and subtract. That cancels out, and then we have negative 3x plus x, which will give you a negative 2x, which means that you can further continue to divide. It goes in there negative 2 times, so negative 2 times x would be negative 2x plus 2. We're going to subtract, that goes away, and that leaves you with a remainder of negative 2. We can't further divide, but what it means is that here your quotient there, that is where your asymptote is at, so that will be at y equals x minus 2. So if we come up with a quick sketch of this, let's go ahead and do that. We know that we have an asymptote at x equals 1, a vertical asymptote, and a slant asymptote at x minus 2, so that would be something like this. Okay, so remember, we just want a rough sketch. We don't want the exact graph, okay? Now, we're interested as the limit as you approach, as x approaches 1. So a couple scenarios that could happen, maybe that both of the graphs go like that, or one goes up and one goes down. So we're going to have to find that out real quick by just plugging in a value other than 1. So let's say that we plug in 0. So if I plug in 0, that would be 0 on the numerator, over negative 1, which is just 0, which means that my graph should go through this point, and according to the definition of asymptotes, then it should be following that way, and should be following that asymptote there. Now if I plug in 2, I get 2 minus 1, which is 1, so I get 1 on the denominator, and then 2 squared, which is 4. 4 minus 6 is going to be negative 2, so I am going to be located at negative 2. So that would be somewhere down here, which then gives me the idea that the graph should look something like this. So now I can analyze this graph to answer the question. So the question was, what is the limit as x approaches 1? Well, as x approaches 1 from both sides, notice how one side I'm going to positive infinity and one side I'm going to negative infinity. Therefore, we can confidently say that the limit as x approaches 1 of x squared minus 3x divided by x minus 1 does not exist. Okay, now we're going to move on to finding limits at infinity. So what does it mean at infinity? Look at the problem or the example that we're going to do. This time, the answer is not infinity. I am asking you what is happening as you approach infinity. Okay, so here's where things get a little bit tricky. Okay, infinity is not a number. It is a concept. Therefore, our techniques that we've previously used of substitution may not be a good idea. And I say may not be a good idea because you can attempt it, okay? Now, here's what I mean by that, okay? You are more than welcome to try to plug in infinity for x. So what happens here is infinity squared would be infinity, times 3 would be infinity, and everything's nice, we're good. Infinity squared is infinity, plus 1 is still infinity. So you may be tempted to say that infinity over infinity is equal to 1, but I would have to say that that is not true, okay? By the way, this is another form of the indeterminate form. Okay, let's discuss why is it not equal to 1. Well, I want you to really think this through, okay? Okay, so you plugged in infinity to both of this and you square them. So yeah, if you square them, they're going to be the same, right? But think about it. If you take this infinity and you multiply by 3, that is going to be a larger infinity than if you take the same infinity and add 1. So we can go into this long conversation about infinity and whatnot. I mean, well, technically they're really large. However, that is the reason why you don't treat infinity as a number. So plugging infinity into the equation may not be a good idea, okay? And I say may not be a good idea because some scenarios it could actually work out, right? But anytime you get infinity over infinity, the indeterminate form, it's going to be an indeterminate form, and that tells you that it's not equal to 1. That is the most important thing for you to recognize, okay? So we've got a couple ways that we can attempt to do this. So number one is we can try to graph this and see what's happening. So that's the very first thing I'm going to show you in this video. Let's go ahead and graph this and see what happens, okay? So first, do we have any vertical asymptotes here? Well, we set this equal to 0. That will give me an imaginary or a complex number which would not show up on a real number graph. So we do not have a vertical asymptote. However, we do have a horizontal asymptote at 3. So y equals 3, we would have this asymptote here. Cool. And now we just have to just plug in some numbers to see what's happening here, okay? So let's say I plug in 0. So if I plug in 0, I'll get 0 in the numerator and 1 in the denominator, which means I would have the point 0 there. Let's say that I plug in 1, I will get 3 over 2. So 3 over 2, by the way, this was y equals 3 right here. So 3 over 2 is 1/2. So 1 and 1/2, I'm sorry, so that'll be about right there. If I plug in -1, I'm going to get the exact same value because of the square. Okay, let's say I plug in 2. 2 squared is 4. 4 times 3 is 12. So we will get 12 divided by 2 squared is 4. That's 5. So 12 over 5. That is going to be more than 2. So that's going to be a little bit closer. And it's going to be the same thing for the negative. So I have an idea based on the definition of an asymptote that this thing is going to look something very similar to this. So now that I have the graph, I feel very confident in answering this question, which in this case is what is happening as you approach infinity. So if you put your pen on this graph and you go to infinity, notice that you will follow this asymptote forever. So in technicality, if you remember from Algebra 2, you approach an asymptote infinitely. So really what it means is that you're getting closer and closer and closer to that asymptote, which means then that the limit for this problem would have to be equal to the asymptote. In other words, the limit as x approaches infinity of 3x squared over x squared plus 1 would simply be your horizontal asymptote of 3. So now that we've done an example, then we can make a generalization about limits that go into infinity. In order for you to get infinity, and if you're dealing with, in order for you to do a limit to infinity, and you're dealing with a rational function, and that function has a horizontal asymptote, think about it. From Algebra 2, you learn that you will follow that asymptote forever, so to infinity. So in other words, anytime you have a rational function, and the limit is, it's asking you a limit to infinity, then the answer will always be where that horizontal asymptote is located. Okay, so let's do a few more examples. I know it looks like a lot, but it really is that quick, and some of these are really hard to see, so I'm going to go ahead and rewrite it for you. So this very first one says, what is the limit as x approaches infinity of 5 minus 2 over x squared? Well, first of all, I can break this up into two limits, if that helps you. This can be the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. Okay. We know that the limit of a constant is always a constant. So in this case, I'm going to go ahead and go this way. We know that the very first limit is just going to be 5 minus. Now the second, we have a rational function. And remember, when you're taking a limit to infinity of a rational function, ask yourself, where do I have a horizontal asymptote? Now, if you don't remember how to find horizontal asymptotes, you can look up my video on rational functions that describes how to find horizontal, vertical, slant asymptotes. So in this case, the horizontal asymptote for this one would be 0 because the denominator is bigger than, the power of the denominator is bigger than the power in the numerator. So that always gives you a horizontal asymptote of 0. So that means it's 0. So that means that the entire limit in this case would be equal to 5. And it's that simple, okay? I'm just going to skip that one because I don't have room. Let's go to 17. It says, what is the limit as x goes to infinity of 2x plus 5 over 3x squared plus 1. So this one I don't really need to break down. I think it's easy enough for me to recognize where the asymptote is located. In this case, we have an asymptote, a horizontal asymptote at y equals 0 one more time because the denominator is bigger than the numerator, and that would be the entire problem there. Okay, this one you cannot break up into the two as I did on the first one because you can't break up the denominator. Okay, all right, let's try number 18. So it says, what is the limit as x approaches infinity of 2x squared plus 5 divided by 3x squared plus 1. But once again, this is very simple just to look at. I'm looking for a horizontal asymptote, and because the powers are the same, remember that to find the horizontal asymptote, you would just compare the leading coefficients. So in this case, you have a 2 versus a 3, which means that your answer will be 2/3 because that is where the horizontal asymptote would be located. Okay. We've got another one down here, which is the limit as x approaches infinity of 2x to the third power plus 5 over 3x squared plus 1. Okay, and it is now that we've run into a problem. Okay, and unfortunately we're gonna have to investigate in a different manner. Okay, notice how the power on the numerator is bigger than the power on the denominator. Therefore, what that means is that we do not have a horizontal asymptote, we have a slant asymptote, okay? Which means that we're gonna have to find out that slant asymptote, or we can graph it, so that we can graph. Okay, so graphically, I mean, I've already shown you an example of how to go about it, so you should be able to graph this if you would like to do this. So I'm gonna go ahead and show you an algebraic way that you can try and do this, okay? So the way that this works is that you are going to find the term, and there is 3 terms here, so you have 1, 2, 3, 4, 4 terms. The term with the highest degree, which in this case is gonna be the x to the third, 2x to the third. Now you can ignore the 2. So what you're gonna do is you're literally just gonna take the variable with the power, and you are going to divide every single term by that. So here's what it becomes. The limit as x approaches infinity. What's 2x to the third divided by x to the third? Well, that gives you a 2. What is 5 divided by x to the third? Well, that's going to be 5 over x to the third. What is 3x squared divided by x to the third? That's just going to be leave you with a 3 and an x on the denominator. And then what is 1 divided by x to the third? Well, it's just going to be 1 over x to the third. Okay. Now, this is where you can use some of the properties that I've taught you in a separate video, which is you can take the limit of each one of these terms individually and then just use the operations to add them and then divide. Okay, so let's go ahead and do that. What is the limit as x approaches infinity of 2? Well, remember, the limit of any constant, it's always going to be the constant itself, so we're going to go ahead and say 2. Now, this is one of those where I am actually going to plug in infinity, and you're going to see how it can actually work out. So, because the numerator is just 5, it's constant, it's not going to change. The denominator is a variable, so if I plug in infinity cubed will be a very large infinity. Now, I want you to think this through. If you take 5 and you divide it by a very, 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 very large number, that's going to give you some very, 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 very small number. So that's going to be like 0.000, like a lot of zeros and then something there at the end. Now remember, we're taking limits, so we don't really care what is happening at this value. It's like what is happening as you're approaching it. Well, if it's so small, we can say that it's approaching 0. Okay, so that means that for this one we're going to get 0, for this one we're going to get 0, and for that one we're also going to get 0. Okay, so we have an issue here. Okay, because we can't divide by 0. So we're going to go ahead, and I just realized that I told you the wrong thing, and I apologize, this happens. So let's go ahead and fix it. I don't really want to edit this video. Let's go back to this step. My apologies. I now remember what it is that we need to do. You need to divide, I am so sorry, by the highest degree term on the denominator. So you will ignore the numerator. You will only look at the highest degree term on the denominator. I apologize for that, okay? So if that term is x squared, so we would take 2x cubed divided by x squared plus 5 divided by x squared, and then we have 3x squared divided by x squared, and then we have 1 divided by x squared, okay? So we're going to go ahead and clean that up so that the limit as x approaches infinity. So that's just going to leave us with a 2x here plus 5 over x squared over 3 plus 1 over x squared. So now think this through. Once again, if I plug in infinity for this 2 right here, those are just going to go to 0. So I'm okay with that. The limit of a constant itself is always going to be the constant. So 3 plus 0 is 3. Now we're game. Now think this through. If you were to plug in infinity here, right? So infinity times 2 is just going to give you an infinite number. Okay. So this is where it's okay to use the idea of substitution. So if you do infinity plus 0, I'm sorry, it's just infinity, right? But if you're dividing by 3, infinity divided by 3, it's still going to be a very, very large number. So it would be totally okay for us to say that this limit would be equal to infinity. Okay? All right, let's try one more to make sure that you understood that. So sorry for the confusion, and then that will be all for today. So this last one right here, it says, what is the limit as x approaches infinity of 2x squared minus 4x divided by x plus 1? So one more time, I recognize that the numerator has a higher degree than the denominator, so that means we are going to be able to recognize that this is a slant asymptote, so we can use the technique that I previously used. So I'm going to look at the denominator, and the highest degree term is x. So I'm going to divide everything by x. So I'm going to rewrite this as the limit as x approaches to infinity. 2x squared divided by x would give you a 2x. Negative 4x divided by x would give you a minus 4. X divided by x would give you 1. And then 1 divided by x would give you 1 over x. So I'm going to go ahead and try what we did on the previous example. I'm going to substitute or think about trying infinity here. So infinity times 2 is just going to be infinity. The limit as x approaches infinity of negative 4 is just going to be negative 4 itself. The limit as x approaches infinity of 1 is going to be 1 itself. And then the limit as x approaches infinity of 1 over x is going to be equal to 0. So think this through. Infinity minus 4 is going to be infinity. And then 1 plus 0 is going to be 1, so that's just going to give us some type of infinity. Okay? So recognize that with the slant asymptotes, when you are taking limits to infinity, your answer is either going to be infinity or negative infinity, because I could have said negative infinity here. It all depends, so just make sure that you pay attention to whether I'm asking you infinity or negative infinity. Okay? Again, I apologize for the confusion on this part right here. Thank you for watching, and if you have any questions, just let me know. We'll see you next time.